Hello everyone, welcome to MindSpan Education. This is another video in the series of calculus and optimization. In this playlist, I was taking a course on calculus and optimization for GATE DA 2026, and till now I have covered topic of function of single variable and limits. So if you have not seen those videos, I would recommend first to go and watch limit, because in today's topic you will need the understanding of limits. So let's start. Today we are going to study continuity and differentiability. Continuity, differentiability. This is our topic for today. So let's start. First, let's understand what continuity means. Let's take an example. Let's see this graph. First, we will understand what continuity or continuous function means. Then we will see how we mathematically derive continuity and how we check whether a function is continuous or not on a particular point or in an interval. So let's take an example. This is a graph. Graph means function, and we have this function from A to B. So as you can see, there is no missing point in this graph from A to B, and you can draw this graph without lifting your pen anywhere during the course from A to B. You don't need to lift your pen, and in one stroke you can draw this graph. So this kind of graph, this kind of function is called continuous function, where we do not see any missing point, we do not see any breakage in the graph. So this is called continuous function. Intuitively, this is how we understand what continuous function means. Means the graph is continuous from starting to the end point. Let's take another example of discontinuous function. Let's take another example. First, there are several types of discontinuities. So we will see them all first. We are trying to understand what continuity means currently. So this is one function. Let's see. And till here we had like this, and this is open bubble, and here graph jump to here, and this is right side of the graph. And this graph is from A to B. This is X and this is Y. This is Fx. So clearly you can notice here, let's call this point as C. Clearly you can see here at point C, there is a jump in the graph. You cannot draw this whole graph, whole function, starting from A to B without lifting your pen. Till here you can draw. After that you have to lift your pen and then shift at higher point here at close bubble, and from here you can draw rest of the graph. So in one stroke you are not able to draw this whole graph. So this type of graph, this type of function is called discontinuous function, and particularly this type of discontinuity is called jump discontinuity. Jump. Graph has jumped at x equal to c. Jump discontinuity. Now there are other types of discontinuity also. Let's see. Second type is, let's take another example. Second type of the discontinuity is, it is called point discontinuity, or you can say removable discontinuity. This type of discontinuity in the first example, we cannot remove this discontinuity. So this is also called non-removable. We cannot remove this. This is the property of the graph, and we cannot define this function in any way to remove this kind of discontinuity. Non-removable. Now let's see another type of discontinuity. We are seeing several examples to understand, to get a feel what a continuous and discontinuous function looks like. So let's say graph is like this, and here we have open bubble, and it is further like this. So at this very point, you can notice at x equal to c, we have defined graph like this. There is a hole in the function at x equal to c, and it is going from a to b. So suppose, let's say at x equal to c, if we were just beside c, just close to c, if it was at f1, and this closed bubble, this point is at f2, then at x equal to c, the function is defined as fc equal to f2, fc equal to f2, and anything in neighborhood of c, the function is defined as f1. So you can see this is called point discontinuity. Point discontinuity. And this type of discontinuity can be removed if we define a function, if we redefine this function in such a way that if we say that at f equal to c, take f1, then this function will become continuous. So this type of discontinuity is called removable discontinuity, also called removable discontinuity. Okay. So here in example 1, we saw jump discontinuity. A function can have jump discontinuity which cannot be removed. Another discontinuity we saw in second example as point discontinuity, which can be removed if we redefine the function in different ways. So now there is one more type of discontinuity. Let's see that one. That kind of discontinuity is called infinite discontinuity. I will give you another example. I am taking multiple examples to make you understand what discontinuity actually means. So let's just take a simple example like this. This function has an asymptote at x equal to 2. Let's say x equal to 2. And function is defined like this. Let's say fx equal to 1 by x minus 2. This means at x equal to 2, function is not properly defined. It cannot take x equal to 2 as input. So in this function, you can see at x equal to 2, if we approach x equal to 2 from left side, it is going positive infinity. If we approach x equal to 2 from right side, it is going negative infinity. So here two-sided limit does not exist. If you have seen the limit video, I have already explained what is one-sided and two-sided limit. Here in this particular case, two-sided limit does not exist. So we can say limit at x equal to 2 for this function does not exist. If limit does not exist, means this function cannot be continuous. I will explain later what is the connection between limit and continuity. So this function is discontinuous at x equal to 2, and this type of discontinuity is called infinite discontinuity. Infinite discontinuity. Okay. So let's recap this, what we saw just now. A continuous function is a function whose graph, intuitively how we can say whether a function is continuous or not, whose graph will have no missing points in the interval that we are talking about. So what I am trying to say is, if we are considering an interval from a to b for fx, then from a to b, if fx is continuous, then there won't be any missing point in the graph. This graph will be solid and can be drawn with one strike without lifting your pen. Then that kind of function is called continuous. And if that does not happen, if we have to lift the pen to draw the graph in the interval once or more than once, then that kind of function is called discontinuous function. And discontinuous functions are of several types. First was jump discontinuity that I explained here. Let me change color. Okay. First was jump discontinuity here. Second was point discontinuity. Point discontinuity means one or many point of the function is defined separately or missing. We can remove this kind of discontinuity by defining this function in separate different ways. So if we put this function as this point as in redefinition, then this function will become continuous, as we will not have any missing points. If we fit the missing point in the graph, then obviously there won't be any missing point, and the graph will become, the function will become continuous. And the third type is called infinite discontinuity. Here we have vertical asymptote. Asymptote means this is a tangent at infinity. This is called asymptote. Tangent at infinity for a graph is called asymptote. So at x equal to 2, we have asymptote for this graph. And one side of the asymptote is reaching positive side of infinity, and another side is reaching negative side of infinity. So here clearly, if you see intuitively, this graph has broken at x equal to 2, because at x equal to 2, if we move slightly towards left, we get positive infinity, and if we move slightly towards right side, we get negative infinity. That means you can see how much change drastically happened by just slightly changing, moving in the neighborhood of x equal to 2. So this is infinite discontinuity. Now this is how we intuitively, by seeing the graph or by looking at the function, we can intuitively think that whether function is continuous or not. But all the time we do not derive or reach the conclusion about the continuity for a function intuitively. We define a mathematical formal way to have a some formula kind of thing, so that we can check whether the function is continuous or not. So let's talk about formal definition of continuity of a function. So how we define that? Formal definition, or you can say mathematical definition. This is also called 3-step continuity test. 3 steps continuity test of a function. How we do this? Let's see. Okay. First, what we do? Suppose, let's take an example. Then only we will understand. This whole chapter we will understand by example. Otherwise, we won't get the feel about what is happening. So let's take an example. Let's take first example. Limit function is defined like this. This is a piecewise function. I've already explained what is piecewise function in very first video. So if you have started this playlist from here, then I would recommend to start from the beginning. or if you are understanding, then it's fine, you can continue. So let's take an example. Let's say fx equal to x square when x is less than 0, and fx equal to x plus 2 when x is greater than equal to 0. How we check this function? First thing, we can draw the graph and we can see whether we are able to draw the whole graph in one strike or not. But here interval is very big. It is from minus infinity to infinity. So we cannot check by drawing the whole graph from minus infinity to infinity. How we will check? We will try to find probable point of discontinuity. So first let's draw the graph for this function. Let's see what it says. First part of the graph is this. So completely, let's draw completely. So this is y equal to x square. This is x square function, right? And this portion of the graph, I am drawing complete graph, and then we will cut it and we'll take only the side we are defining through this interval, x plus 2. So it's like starting from here, x equal to y equal to 2 or fx equal to 2, and from here it's a 45-degree angle line. So this graph is like this. Now what this graph says, that this piecewise function says that for x equal to less than 0, we have to take this graph. So if I take here, this is x equal to 0. So for left side part, we have to take this part of the graph. And for right side, x equal to greater than 0, we have to take this part of the graph. So let's combine this first. What we will get? We will get, let's see. Let's combine this based on our piecewise definition of this graph. So left side graph less than 0 will be like this, right? And right side, it will be starting from here. And here we will have open bubble, because x is greater than equal to sign is with this portion of the graph. So closed bubble will come here, and it is like this. Now, by just looking at the graph, you can clearly say that there is no possibility of the graph to be any point of discontinuity from this side, and no possibility of the graph to be discontinuous on this side. But at x equal to 0, we have a culprit. At x equal to 0, we can see graph has jumped. You can clearly see there is a gap in the graph. If we start drawing from here, then at x equal to 0, we have to lift the pen and move at here and then start drawing again. So at x equal to 0, there is a jump in the graph. So this function is discontinuous. First, we deduced this by the graph and intuition that this graph is discontinuous at x equal to 0. But how we mathematically find this? So why we plotted this graph? To find out suspected point. So x equal to 0 is the only suspected point for this graph. So we will check only discontinuity at x equal to 0. How do we do that? We calculate limit of this graph, this function at x equal to 0. So our function is defined like this: x square when x is less than 0, and x plus 2 when x is greater than equal to 0. So if I go and calculate limit of this function, left hand side limit, which will be limit x tends to 0 minus fx. 0 minus means less than 0, slightly less than 0. So this part of the graph will come. So it will become limit x tends to 0 minus x square, which is 0 square, and it will become 0. If we calculate right hand limit, this will become like this. Limit x tends to 0 plus and fx. So it will take this portion of the graph, x plus 2 part of the graph, and it will become limit x tends to 0 plus x plus 2. If we put 0 in this will become 0 plus 2 and 2. Now here we can see that the left hand side of the limit does not become equal to right hand side of the limit. So we can say two-sided of the limit does not exist. Does not exist, which means we can say that limit x tends to 0 fx does not exist for this function. So if limit does not exist, then we can say function is not continuous at that point. But what we check actually is, we check that in 3-step continuity test, what we check is, we check limit x tends to a minus fx equal to limit x tends to a plus, we are checking at x equal to a. For this formula sake, fx I equal to f at a. This is 3 steps. This is first step, this is second step, and this is third step. All 3 should follow this condition. Then only we can say that function is continuous at x equal to a. Here we can say fx is continuous at x equal to a if this condition holds. So if left hand limit equals right hand limit and the function is defined at a and equal to fa, then we can say that function is continuous at x equal to a. Continuous. So this is how mathematically we try to verify whether function is continuous or not at x equal to a. So now let's take the example. What example we here had? Here we had LHL as 0, 0 and RHL as 2, which means we need not to check function now, because LHL and RHL must be, for the first thing, these two should be equal first. If they are not equal, then there is no point in checking function's value. Here they are not equal, so whether the function is defined at x equal to a or not, it does not matter. This function anyway not going to be continuous, but function at x equal to 0 is 2 here. Now let's take another example to get better understanding. Let's take another example. Let's take this another example. Let's define our function as fx equal to, this is also piecewise function. In continuity and differentiability, you will mostly get piecewise functions to check whether continuous or not. Let's say this is x when x is less than equal to 1, and this is x cube when x is greater than 1. This is the function. Now if we try to check this function, continuity at x equal to 1, since if it is less than equal to 1, for all the value less than or equal to 1, if we do not consider the value x equal to 1, then for all the value it will always remain for x is less than 1. it will always remain fx equal to x. So no need to check all the point less than 1. And for all the value greater than 1, this function will become fx equal to x cube. So linear function, cubic function. It is like polynomial, and we are not going to get any missing points. So this will also be continuous. So only suspected point is x equal to 1. So we will check at x equal to 1. How we do that? First we calculate left hand limit. Limit x tends to 1 minus fx, which will become limit x tends to 1 minus, and 1 minus with, we have to take this part of the graph, fx equal to x. So this will become 1. And right hand limit, we will get limit x tends to 1 plus fx. This will give us limit x tends to 1 plus, and right hand means x is greater than 1. So this part of the graph, x cube. So this will give 1 cube, means 1. Here, as you can see, we have gotten both part as 1. So this is like good starting point for a function on the path of becoming continuous. So now we will calculate function at 1. So equality sign is here. So at 1 we will get 1. Here you can see both LHL equal to RHL, as well as function is defined and equal to 1. So we can say that fx is continuous at x equal to 1. And for other part of the graph, in other part of the domain, it is also continuous. So this function is continuous in whole domain, right? So this is how we find the continuity and differentiability. Differentiability I will cover in next video. Otherwise, this will become very long, lengthy video. So in next video, I will take few more example on continuity to give the clarity, and I will cover differentiability. And one more small announcement for you guys. We are happy to announce that we have launched GATE DA test series for 2026. All the aspirants who are going to appear for 2026, we have launched a comprehensive GATE DA test series, and this test series is accessible at our website MindSpan education.com. You can go here and check the detail about the test series. It is very comprehensive test. We have included quality problem, more than 1400 quality problems, 1400 plus quality questions, more than 60 plus tests we have, and comprehensive solution for each question. And we have invested a lot of time to formulate these questions. All the question will give you some learning, and I'm sure after attempting the test series, you will have a better understanding of the topic, and it will definitely help you achieve better ranks. So go to mindspaneducation.com and explore this test series. Also, we are covering different series, video course, linear algebra and probability. So you can also go through those chapters. I will give the link in the description of this video. You can go and watch this free video course. Thank you everyone. In this video, this much only. In next video, I will cover differentiability plus few more example on continuity and differentiability. Thank you everyone. Happy learning.